Hello, my name is Arjun Verma, and today I'm going to go over my second lab for Physics 2112, the sophisticated version of the charge tapes lab. So first, introduction and purpose of the experiment. So the purpose is to utilize charge tapes to explore the electric force and how it works in our environment, and see how it interacts in reality with household items. Introducing a more sophisticated model to evaluate the charge tapes and their dynamics is also the main purpose of this lab as opposed to the previous one, because it lets us see a better version of how we can calculate the charge on the tapes. And the main thing that we're going to be considering today is the fact that electric field is equal to kq over r squared, and also that electric force is just the field multiplied by charge. So the process of the experiment and the results. So on the right, that's me with the floating tapes, and after conducting multiple trials, I concluded that one 10 centimeter length of tape caused another 10 centimeter length of tape to float at a height of 1 centimeter. And based off the density that was given, the mass of both pieces of tape was 10 grams, just making the gravitational force about 0.1 newtons, right? So therefore, the magnitude of the electric force on the floating tape was also about 0.1 newtons. And this is clear because we're only considering the electric force as the other force acting on the tape besides gravity, and since the tape is floating, they must be in equilibrium. And I found that the tape floated on average at a height of 1 centimeter over all of my different trials. So yeah. And now I'm going to go into the modeling a bit. So utilizing GlowScript and the values I calculated from my experiments, I was able to create a sophisticated physics model to mimic my experiment and calculate the point charges of the tapes. And the main purpose of this model, or at least how it differed from the previous one, is that it considered line charges instead of point charges. And line charges distribute the charge throughout the entire piece of tape as opposed to treating the tape as one point charge, therefore making the model more accurate to reality because it's, not reasonable at all that the tape would just be one point charge. It will be multiple different ones. And on the left, you can see kind of how that acts on it, where the yellow arrow is gravity acting on it, and green represents all of the different line charges acting, whereas the gray one is the net electric force. And as you can see, the electric force and gravitational force are equal with a distributed charge of 7.79 times 10 to the negative 8, which is, the charge of the tape as it's distributed across the tape. And that charge is what allows the tape to counteract gravity by generating an electric force. Right? So kind of going into the results, in order to conclude that the magnitude of the EF was equal to the gravitational force, i.e. when both were applied in opposite directions, equilibrium was reached and the tape floated, and also calculate the line charges, we had to make a couple of assumptions. So we had to assume that air resistance played zero role in the tapes floating. We had to assume that each tape was a line charge or a collection of point charges, as opposed to just assuming that it was one point charge. We had to assume that no other point charges were acting on them and introducing new electric forces. We had to assume each tape had the exact same amount of charge, and we had to assume there was no dipoles or other electric field producers nearby acting on the tapes. So we kind of had to treat this as its own isolated experiment that was in equilibrium and not consider anything else that may have been acting on it. And we also had to assume that they were line charges, which, albeit is a more accurate assumption than saying that it was a point charge, is still not perfectly ideal, right? So kind of going into exploring the results, if we had calculated the charge as a point charge as opposed to a line charge, we would have calculated a charge of about 6.33 times 10 to the negative 8 as opposed to 7.79 times 10 to the negative 8, which is a 23% change. And on the bottom, you can see here, like the purpose of a line charge, it's kind of distributed across the whole tape. So you can see, the mathematical model is different, and we see that the values are different as well. And kind of explaining why these things differ. So as I said earlier, the estimates are models of what is happening with the electric force, and these models differ. However, the line model is more accurate than the point charge one because it realistically models how a flat object acts as a charge. That the charge is distributed across on it. And because the model is fundamentally different from what the point charge is, as opposed to just calculating one, you're going to end up with a different result. And that's kind of one of the main reasons why these two things differ. And that was, kind of the whole purpose of the lab, was to see how this was different from the previous lab and reuse the experiment but have a different physics model behind it, which explains, why the lab was so interesting. So in this lab, we explored how the electric force works in real time and in real life through a floating tape experiment, and we used a more sophisticated model that considered line charges to determine the charge of the tapes. And I had a lot of fun learning about it and seeing how, my observations line up with the models I developed, and also seeing how this was different from treating the tape as a point charge, because it shows just how important the differing aspects and views you have on reality and different models you use are in, the actual interpretation of the results. Thank you so much. This was Arjun Verma, Physics Lab number 2.